So, welcome to the training series of puzzlers. So today we are going to talk about searching techniques. So what about searching? Searching is an important solution for our questions. So usually it is used when we want to find the result from something, let's say minimum or maximum, or the best solution for the question. So we can divide the searchings into different approaches. Complete search, which we are going through this today. Okay, greedy. We also will be going through this today. So the other tools we'll go through them some other days. So which is divide and conquer, which is binary search, an example of it, and dynamic programming. So complete search. So basically, complete search is your brute force to test out which solution is the one you want to find in the search space. So we'll go through it in the questions later. And actually, we are using it on daily basis, which is to find a maximum and minimum number of values I told before. Then find a combination of value that fits the question. So in complete search, we have the types: linear scan, depth first search, usually with backtracking, which I will talk about it later, and breadth first search. So linear scan, we can actually go to these questions and the solution is with this question. So the question is, okay, so some of you might do it before, but let's go through it again. So basically for these questions, you are required to find the maximum number. So the story goes like this. I have this scary costume guys, scary costume guy. So each of them will have number of move speeds that is given by the questions. So let's say for the sample input. So the questions wants you to find that you need to help the counts that none of them will get caught by the scary guys. So if you understand the question, it's very easy. Basically asks you to find the maximum number of the value. So given the list of value, find the maximum value. So this is linear scan because we are scanning through 1D array and it is O(n) time complexity, which means that if we have n data, then we need to find out the value with this complexity O(n). If we have m data, then we need to go through n data. So the question is quite easy. Maybe I just demonstrate here. So first, we read the input, then okay, if you have any problem, you just leave a comment here. I will try to check it out from time to time. Okay, so the first input is a number of cases and followed by the list of the numbers. Test case count. We read the first line, then convert it into an integer, and we are looping through every single line of the test case. So we need to import the IO exception. Then next, we use the string tokenizer to tokenize the values. Next, what we want to do is to store the numbers into an array so that we can use it for comparison later. So the first number here means the numbers that you are going to get. If 5, then you will see 5 number followed by the first number. So the line will have 6 numbers. So I will create a string, integer array to store the numbers. So there we have it. We have the numbers stored into the array. Next, we need to create a variable which is max for our first number. Because max is already our first number, so we should start with second number onwards. If we have no second number, then this loop should not start. Because 1 is less than 1, which is not, which is returns a false. So this loop will not run. So for this case, we should run the code should run here, then skip the loop. So for the comparison to get the max value, actually we have this functions to help us so that we don't have to code ourselves. So the operation goes like this. First we have 9 as the max. Then we compare it to 3. If 3 is more than 9, then we set it to 9, but sadly 3 is not more than 9. So 9 is still the maximum. Then 5, 2, 6, and so on. So in the end, you need to print out the case. So this question is about searching the maximum, the linear scan. Okay. So let's go back here. So I have another question to share, which is UVA 1237. So maybe we just see the questions. So what we did just now was to find the maximum value. So for these questions, you are given a list of car. So okay, the input is like this. Okay, so I have this test case, number of test case. Then followed by the number of car. Actually not number of car, but the should be number of car. Then followed by car, model, minimum price, maximum price. So for these lines, they follow the number of car which is on this line. So this is the number of value. So your job is to find, even okay, I have 60,000. I want to find a car which satisfy the name of the maker. So which is in the range. So let's say for BMW. So our budget, this is the budget. So our budget is in the range from BMW. So for 7,500, we will have Chevrolet. For 5,000, undetermined because there is no car that can satisfy the range. And 10,000. So you should note that if you got two or more makers that satisfy this condition, you also need to print undetermined. So the questions here is quite simple. You can, in my case, I can use a hash map to store the value. So we can use back this. We can create a hash map minimum. And the question say the name of the maker is in single words, so you should not have problems in processing or input. So it's the input is built quite easily. So next, number of cars. We read the next line. So in order to separate the value, we need to organize it. Okay, so this is the name hash, our minimum value. Just copy and paste here. So now we have the list of cars with the minimum and the maximum value. Next. So temp is to store the number of values that we want to find, or maybe we just use number of values here. Okay. So now we got it. So this is our value. We'll look through every value. So this is to get the car name that satisfy the range. So first we get 60,000, then we will look through and see which car that satisfy this condition. But we also need to consider if more than one maker. So I will put a count here. If we get the minimum value from the hash table, which our value should be larger or equal to, and it should be less than or equals to the max. Then we will change the name to this car name. Then we add the count. So what we will get at the end here is the last car that satisfies this condition or this range, and the number of cars that satisfy this condition. So if count equals to 0 or count more than 1, so we should print undetermined. Else we can proceed to print this value, which is the name satisfy. So this is another example for the complete search. Basically, you get a value, then I go through every card that I got it. So next. However, if you have more complex problem, we will run into an issue with time complexity. So in this case, we are actually running at O(n) square. So for each value, we need to go through 4 times. So for the second value, we also need to go through 4 times. So eventually, we will get nm value. So to sum it up, we consider this as O(n) square. So for 4 and 4, then we will get 16. So now we can go into the more advanced questions. Project Euler 32. But before going back, just a quick recap. What we got here, the horror dash is we have these movement speeds. and so on. So what we need to find is the maximum value. So here we need to find the one which has the number that satisfies the range, which is the minimum and the maximum value of the car that we solved just now. So both questions, for these questions, we need to actually go through the data given entirely, so to ensure that we get the maximum value or the value that satisfy the condition. So now we go Euler 32. So let's explain what is pen digital number. So pen digital number is the number that repeats. The number of digits of the number should not repeat. So let's say, so this is pen digital because each of these digit doesn't repeat. So this is not pen digital because 6 repeats 2 times. So the questions ask us to find the combination of the pen digital number that forms this equation. So which is given A, B. So if we concatenate them into string, then they are pen digital. And they also satisfy this equation. So on first thought, you might think, okay, I can just look through 1, 2, 3, 4, 5, 6, 8, and 7, 8, 9. Because the question asks 1 to 9 pen digital. So it should have 9 digits. Another solution, which I will explain later, will be faster. Let's see this next solution first. So we look from here, from this number to this number. So the numbers are actually 864 million. So we also need to check whether the number is pen digital or not. If it is yes, we need to consider two cases. 2 digits number times 3 digit number equals to 5 digit number, and 1 digit times 4 digit equals to 5 digit number. So we need to split them out. Then we check again. A times B is equal to C or not. If it is yes, then we need to check whether the C is added to the sum or not. Because the questions ask us to get the sum of the product, which is shown here. So the questions also say some products can be obtained in more than one way, so be sure to include it once in your sum. So in this case, because we know that the number is in certain bound, so we can use a Boolean flag to check whether we have already added it to the sum or not. So what's wrong with this solution? The time complexity for the number look from here to here is on, so you need to check through n numbers, and the time complexity for checking pen digital is on because we need to check through the digits, so which I will show it later. And to split is on is just simple multiplication. So for checking, assume we are using the Boolean array, so it is fine. And in the end, what we get, we need to consider this and this. So this will give us n square, but our n array is already 864 million. So apparently it will give us a big trouble. The runtime is going to be long. So for exercise purpose, I will just show the code here. So I will create a function is pen digital. This is the naive way. If my number is pen digital, so I will first open a flag, then so we are extracting the last value from in each loop. If the digit isn't exist yet, so the flag should return false. So if it returns true, then we will say it's not a pen digital because the number repeats. Else, true. So put the value here. So we need to divide it by 10. So now we have marked our last digits to the flag. Then we also need to consider the case where it's not pen digital, but it appears here to be pen digital for this question because the question needs 1 to 9 pen digital. So we need to have 9 discrete numbers. So we will just put it here. Once we got a new value, then we add the number. Then in the event we compare the number whether it's 9 or not. If it's 9, then it should return is pen digital. So this is a general one for our loop because we are looping 9 digits to 9 digits. So it should be okay. So it should be no issue on this thing. Actually, we can do this. So it will still works fine because we are doing 9 digits. So for safety purpose, we just put it back and okay. Now for the C, we should divide the number. We get the modular of the number of 100,000. Then it will use the last 5 digits. Then we divide it. So we are finding the next digits. Next 3 digits, so we should divide it by 1000. So the remaining value should be A. So if A times B equals to C, sum. But we have two parts here. So this is the first value, and this is part 1. So for part 2, we will modify the value slightly because we are using the and I again, so we should use a 10 for this part. Okay, so we do the same thing. So for this round, we are getting the last 4 digits. If so, if either one of them satisfy the condition, then it is the solution we want to find. So in order to check whether it's added to the sum or not, we know that C maximum value for C is this thing because it is 5 digits. So we can use a Boolean array which is 100,000 and it still fits the condition. If flag C is not added to the sum yet, then we add to the sum, and this is our sum, and we add here C. So I think we should do it here. Okay, so this is the solution we want to find. Then in the end, we display the sum. So that is it for this question. We check whether it's pen digital or not. Then we split into two parts. The first part, the last 5 digits, and the next 3 digit to the first 2 digit, and the second part, 541. So in the end, we check against this condition. Then we check if it is not added to the sum by using the Boolean flag. Then we add it to the sum. Then we print it. So I'm not going to run it because it takes a long time. So let's see the next method, which I use depth first search. So sometimes it's good to view the question from different viewpoint. So the workflow is like this. We generate 2 pen digital numbers, then we generate 3 pen digital number, which is also pen digital to 2 digits just now. So by doing this, we can eliminate a lot of values that we do need in here. So which we waste time on checking is pen digital of those users number. Instead of doing that, we form the pen digital number ourselves. So this is by depth first search. So the working mechanism is pretty similar, but we are generating pen digital this time. So the second part, one digit pen digital, for sure one digit is always pen digital, and generate 4 digits, and then we multiply the value up. We check ABC are pen digital numbers or not, which is also, we can reuse these functions. If C is not added to a sum, then add to sum. So let's just explain how depth first search works. So let's say I have A. So initially my A is nothing. And for A, we can have here. So we have 1, 2, 3, so on. So these are the choice we can go for. This is for the second part, single digits. So next, in order to generate B, we also can use the same methods. One, 2, 3, so on, 9. Because we want to generate 1 to 9 pen digital. So in order to generate 2 digits, we need something called backtracking, which means that we need to keep track of the value that we have generated just now. By doing so, we can eliminate using the is pen digital function every time. So just like the solution just now, we can use a flag. So once we have 1 generated, then for the next, we should not generate 1 1 again because it's not pen digital. So we can proceed 1 9. So how are we going to do that is to for loop from 1 to 9 again and check whether for that number we have the flag marked as false or not. If it is false, which is true for the first in the loop, then we found it, okay, this is a suitable candidate, then we can go ahead and take it. So just a simple illustration. So we need to control the depth. So this is a flag. If our depth is equals to 2, which is 2 digits in this case, so we should have another. So we print out the value, otherwise we for loop it. So we need to check. Okay, so digit is not taken, so the fact should return false. So we add the value, set the flag to, and we call the function again. So in this case, our depth should be +1 because we are now a level lower, and flag value. So after calling this, we should mark the flag back as false. Otherwise, we'll end up run into the condition like I've 1, 2, and I didn't clear the flag, and when I go here, then I could not go here because our flag is already set here. So we can't go back to here. So we should set the flag to false. So let's just run this value. Our depth is starting depth is 0. Then our boolean is 10. So seems like it's not stopping. So let's see what's the issue here. Okay, so got the problem here. So I should update the value. So as you can see from here, the value that we are generated are actually non-repeating digits. So 1, 2, 1, 3, 1, 4, 1, 9, 2, 1, and there's no 2, 2 because when we try to put 2, 2, and we found that the fact is actually true, which means that the digit has been taken, the digit 2. So we should not take that path. So in order to generate B, once we have A already, so in order to generate B, we should do something here. We can create another function for generate B. And once we have generated B, then we can get C. Then we check C against the pen, A and B, whether when they are combined, they are pen digital numbers or not. Then we can proceed to do this. So by using in the backward search, because we could go something like this, but we didn't. We use backtracking to cut out this branch. So if you want to know more about this question, you can go to GitHub to get the source code. So this is the difference, 2 digits and 3 digits. We got 5, 9p5 each. So given 5, we need to find 5 digits here. So we have 9 digits to find. So it should be 9p5, and because the arrangement is important, so it's P not C. And to check the pen digital number, ON, just like this one. And to sum it up, we multiply them up, and what we get is just 272k of operation as opposed to this 864 million. So the difference is quite there. If so, this can be achieved if you see the questions in different viewpoint. So this is the detail. We have volume flag. Then we know what digits to take. So we eliminate the redundant digits where we don't need, because it's pointless to continuously doing the operations, extending the things here because they are impossible to be the solution. So we might as well as just cut it off early so we can save the time. So another questions UVA 441 which also use the same idea. So given the list of numbers here, you need to generate all possible cases and they need to be sorted. So for this method that I have illustrated just now, we are running on the smallest to largest value 1 to 9. So the number that we have generated should be from smallest to largest in ascending order. So given you these 7 elements, you need to find out to list out the permutations of this value such that they do not repeat each other. So it's quite big here. Okay, so I will leave these questions to you. So it's something like this. So the also have the issue for depth first search. The time complexity for normal depth first search is O n power by m, where n is the choices we can go, and depth. So for binary tree wise, we have 2 fan out and n depth, so the complexity for it is 2 power of n. And if we do it in recursion way, just like this, every time we call the functions, the compiler needs to generate the stack for the value here, so that later we have done doing this, then we can go back here and continue doing the operations again. So you might do it in iterative way, which is for loop. So another way is iterative deepening depth first search, which we limit the depth of the search. So there's a questions in project viewer. So if you ever reach it, yes, you can use it. So so the linear search and depth first search are actually complete search. We search through all the possible solution and find out the one those we want. So another one is breadth first search. So unlike the depth first search, we go from one level by one level. So on the first level we got this, then from the second level we got this. But this is included in the graph chapter, so I will talk about it later. Not now. So the general idea for complete search is it is simple. You just need to brute force the solutions to check whether this solution suits my conditions or not. If yes, then we take it. However, it creates an issue in time complexity. Let's say for depth first search, it is O n power by m, or even this n square. So it's very big. So but if you put it correctly, then you should always get the answer. So the issue often lies on the time complexity. So just now I have tried the next clever search. it's still a complete search, but search space is much smaller because we perform branch cutting through backtracking in order to remove those solutions which is not impossible to be the solution. So the what competitive programming the book say you should watch out the time complexity. If it is 100 million below, then you can use complete search. Otherwise, you can consider using other searching techniques. So which I will share about it later. So now greedy search. So greedy search, as you can see from its name, is greedy. So let's say when we are given the choices, we always pick the one that with the largest value, for instance. So the concept is as simple as that: be greedy. However, greedy has its own limitation. So we need to identify these two properties: suboptimal structure, which means that when performing a loop, we need to ensure that the choice we pick is the optimal one. Let's say I have 3, 4, 5. We need to so for greedy we will pick 5. So we need to ensure that 5 is the optimal structure for the case where we took one coin. So in greedy property, this is important because it often dictates which approach do you want to solve the problem. So for greedy, we don't have to care what we choose previously. So if we choose 5, well, don't care. Another round we can choose 5 and so on. So the famous question, the famous coin change problem is greedy search. Let's say I have 1 cent. So given 75 cents, list out the changes. So what we will take? We will take 50 cents first. Yes, then we will get 20 cents. Then 10 cents done. Then so this is a greedy. Given the choice, we always pick the best one first. Then only we consider the smallest one when the big one is not available. So the example mixing milk USSCO. Okay, so this question is about, let's say I have 100 liters of milk. Then I have the supplier that sells that can receive certain liters of milk, let's say 20, and they receive at the price per liter of N. So N0, N1, N2, N2. So this is it. So our issue is to find the maximum value that we can sell for the milk, which is the money. So our choice in this case is to pick the one with the largest, or the seller that offers the maximum value per liter. after, but he only can get 20 liter. In For this example, we can take, and so we'll pick this seller first. Sell for 20 liters. So remaining we have 80 liters. Then we'll get the next seller which has a maximum, which offers a maximum money per liter. So this seller offers 9 cents per liter. So 9 cents. Sell 10 liters again. Then we do the same thing, so on. So this is the greedy search. The next one is barn repair. So given this list of rooms, then you need to find out the maximum number of the store block, which the store has the counts. You might read the question by yourself. And coins exchange, so which I shown it just now. Choose the largest number of coin to reduce the number of coins. So let's say I'm given 100 ringgits. So I have this. So I can have these changes. So I need to find the minimum number of note that can form 100 ringgits. So in this case, it's 50 ringgits. But you eventually end up running into an issue, which is shown here. Let's say I have 2 cents, 4 cents, and 5 cents. 2, 4, and 5. So we want to minimum the coin to change to 6 cents. So for greedy, if you get us to, okay, I will choose 5 because 5 is the maximum that I can choose. So 5 cents. Okay, so remaining will be 1 cent, but we have no 1 cent. So what happened? No solution. So that's the issue with greedy search. So if you observe this question correctly, it doesn't have this property, greedy property. We don't have to care what we choose previously. But for this case, we need to care that what we choose previously, it will affect our solution. If we choose 5, we need to care about it. If we choose 4, so that's it for the part 1 for the search. So time for some exercises. You can find in the book or you can do it in USSEO.